Please start.
Okay, welcome back. I will pick things up where I left off. You remember the plan of these three lectures. Let me turn the timer on here, sorry. The plan of these three lectures is I'm just about finished the survey of effective field theories, and then I'll do a survey of cosmology with a view to focusing on structure formation, which is where quantum effects are being argued to have been seen, gravitating quantum effects. And then we'll finish with EFT-specific issues that cosmology raises. And again, please interrupt me if you have questions as we go along, because that's a much more efficient way to handle things and to do them at the end of the lecture. And it's also true that there's a lot of material, and in the absence of questions, I'll just go faster and faster and faster, and soon you won't be able to understand anything I say, because I know that I speak quickly. And the beautiful thing about blackboards is that they slow you down, but slides don't do that. So just so you're warned. Anyway, one of the issues that will come up, I'm going to deal with now, as far as regarding effective field theories and cosmology. And that is the issue of time dependence of the background. So people often think of effective field theories as being tied to expansions around the vacuum of the theory, that you identify some static vacuum, you look at the low energy fluctuations around that vacuum, and then you categorize states according to their energy, and you have energy as a conserved thing because you've got time translation invariance in your problem. And you remember that important part of the effective field theory story was we were projecting onto a subset of states based on conservation laws, and in particular energy conservation. So you might think that time-dependent fields could cause a problem for that, because time dependence of the background will mean that the fluctuations around that background needn't conserve energy because you've broken time translation invariance. They can extract their energy from the background. So why isn't that a problem? The reason I'm talking about it now, rather than when we talk about cosmology-specific problems, is I'd like to emphasize that this time dependence issue is not specific to gravity. It's just really true for any time-dependent problem with effective field theories. So if I can advance the slides here. Okay. So I've made the argument that it's naively, you might think you have problems defining effective field theories in the time-dependent situation. And of course, that won't be my conclusion. Otherwise, we'd be in trouble for cosmology. Then basically the short version of the story is that there are some time-dependent problems for which you cannot use effective field theories. They introduce a new class of ways in which effective field theories could break down. In the static case, we already knew that effective field theories would break down if there was not a hierarchy of scales. If light masses were not very small compared to the heavy mass scales, then the Taylor expansion powers of the ratio won't be very good. What time dependence does is it introduces a bunch of new scales. Basically, every field in your problem, or every observable in your problem, is now time dependent. And adiabaticity says that all your observables, the derivative with respect to time of the logarithm of the observable, so dAdt over A for all your observables A. Those are new scales in your low energy theory, and they have to be much smaller than whatever you think your ultraviolet scales are. So that's the new criterion that you have. And what's going on is that because things are adiabatic, in that situation, although energy is not conserved, there is an adiabatic energy which is time dependent. But what happens is that the energy levels, because the background motion is slow, in a snapshot of time, the energy eigenvalues do exist. Energy is approximately conserved, and the energy eigenvalues are parametrically dependent on the time. And that's the way in which you see that they're not strictly conserved. And so then that introduces new things to worry about. So in these plots, if I imagine plotting energy levels, where the upper solid line is the lightest UV state in your problem, the one you're trying to integrate out, and the lower line is I should make this visible here. the lower line here is is one of your states in your low energy theory. They're separated by the dashed line, which is where we're imagining dividing the high energy from low energy parts. Those are all, in principle, time dependent now, if the energy levels are time dependent. So the thing on the left is something which is okay. The division between ultraviolet and infrared might be forced to become a function of time if all the masses and energies are drifting around. And so just because you start in the low energy regime doesn't mean you're going to end up in the low energy regime. Things like gravitational collapse and black holes are kind of clear examples of that. You start from a very, very, very low energy distribution in some cloud of gas. You let it collapse, and eventually you're being driven to a region where you've left your domain of validity of the low energy theory because you say you've got a singularity where everything collapses. So you have to watch that. Another kind of thing that can happen on the right is level crossing is a dangerous thing. If you think that in the left, everybody's drifting in the same way, but if your time dependence is making your high energy states drift down and your low energy states drift up, they can cross it sometimes. And that famously is a place where the adiabatic approximation can fail. Because now the splitting between the heavy and the light state has gone to zero. And that's the kind of situation where that'll also force the breakdown of your effective theory. Typically what'll happen in a field theory is you can imagine masses being functions of time. And if some of them are driven down to zero as a function of time, that means that somebody you thought was heavy is now light. And so you are punished for having integrated it out. You have to kind of start tracking that new light degree of freedom explicitly in your low energy theory if you want to have reliable predictions. Excuse me. Those are the kind of issues you would worry about. Let me turn this dot off here. So I'd like to take you through the example of this toy model, because the toy model shows very concretely how time-dependent systems would work. So remember the toy model, we had a complex scalar field, we had a Mexican hat potential, and we've previously to now been looking at the low energy theory found by expanding around a vacuum of this theory where we expand phi around V, which is the minimum of the potential. When doing that last time, I showed you that the low energy scattering of the degrees of freedom were all being controlled by this effective interaction involving the light field only. There's a massless field and then there's a massive field, and we imagine integrating out the massive field. And the light field has this effective interaction which is capturing to order 1 over m to the 4th all the effective virtual effects of the heavy field in scattering problems. But now let's ask a time-dependent background problem. So rather than expanding around the bottom of the potential, there's also a classical solution where the field rolls around the potential, but it's not exactly at the bottom. So we look for a solution of the form that's written here. Let me put my laser pointer on again. So this the form here we'll take phi to have a constant modulus, but a phase which is linear in time. That's a solution to the equations of motion, but it's only a solution if the frequency omega and the value of the modulus rho naught are related to each other in this way we're written at the bottom here. You see that if omega were 0, then rho naught would be V, and that's the solution where you sit at the bottom and you don't roll. But the fact that this square root is bigger than V whenever omega is not 0 is showing you that what happens is physically intuitive. That you climb the hill. If you're going around, you're climbing the hill because the potential has to provide the centripetal force that keeps you moving in the circle. And the faster you move, the more force you need, so the farther up the hill you climb. So the classical solution kind of does everything you expect it to do. All your intuition, your classical intuition is true for this classical solution. So now, if you look at the energy of that solution, it's given by this expression here. It's got a kinetic term and it's got a potential term. And so you can see that it has a piece, it vanishes when omega is 0. But the second term in the right-hand side, the 3 omega squared over lambda, that is getting 2 contributions. One of those, I think 2, that number 3, you can think of it as being 2 plus 1. And I think the 2 is coming from the contribution of the kinetic energy of the motion. And the second, part of that energy is coming from the fact that you've climbed the potential a little bit. And you had to climb the potential because that was required to make the forces balance. So the question in the effective field theory is, In the effective field theory, we don't have a potential. All we have is this derivative interaction for the light field. How does the effective theory know about the energy associated in the full theory of climbing the potential to make the forces balance? So what we'll do is we'll just take the effective theory the way we figured it out and ask what's the corresponding solution and what's the energy. And so the solution to the equations of motion in the effective theory will just be something linear in time. That variable c will be just omega t. And we can ask what's the energy in the effective theory of that solution. And this is what it is. It's got a piece coming from the kinetic term, and it's got a piece coming from that effective interaction, the 1 over m to the 4th interaction. And I've used the specific numerical coefficient that scattering told us had to be there for that. And when you evaluate the energy using both those terms, because the derivative picks up a factor of omega, you see that you get the same structure as you had in the full theory with the same numerical factor. And the reason you get the same numerical factor is because of the choice of the coefficient in front of this 4 derivative term that we had before. So this effective interaction, this 4 derivative interaction in this context is capturing part of the energy or part of the kinetic energy of motion of the full theory, including pieces to do with the climbing of the potential in the full theory. And this kind of emphasizes that we didn't have to adjust the coefficient of that interaction to make it work. The low energy expansion works for all observables at once. You just do it in the Lagrangian, and then you can apply to any observable. And this kind of verifies that in the sense that we identified this effective interaction using scattering arguments around a static solution, but it, for free, provides you with the proper energy of a proper description of a classically rolling background, including its energetics. Ultimately, this kind of a reasoning is kind of what you're going to do in cosmology, that we're interested then in that case in time-dependent background fields. There are going to be gravitational backgrounds, but that's the only real difference. We'll have to be careful that we're within the adiabatic approximation when we do that, and that'll require the say the Hubble scale to be a low energy scale rather than a high energy scale. But the procedures that we go through in many ways are the same as they were in this toy model. Okay, so that's what I wanted to say about time dependence of the background for now. And then I wanted to close with a few examples, just because some of them are, it's always good to see examples you already know, but also there's, again, some relevance to gravity, lessons for gravity that can be drawn from other interactions. So the Standard Model is the poster child of all this, that many of these tools are derived in understanding the Standard Model. Famously, weak interactions that we know are charge current weak interactions are produced because of W exchange, and we know that at low energies that weak interactions had been described by the Fermi theory, and we also know that integrating out the W boson in the Standard Model reproduces the Fermi theory with the specific prediction for how big the Fermi coupling is in terms of microscopic properties like the mass of the W boson and its coupling, G. So that's a kind of a familiar example. Electromagnetism is also kind of provides a familiar example, and it's kind of a useful example to think about when we're thinking about gravity. Famously, one of the interesting things about electromagnetism is you're tempted when you first learn quantum field theory to think that electromagnetism, the field for electromagnetism will be a 4-vector field, the vector potential, and that's actually not true. When it's a solved problem. Which fields can represent which particles of which kind of spins can be represented by which kinds of fields. Weinberg solved that in the 60s. And for a massless spin 1 particle, the solution is not a vector field, it's actually a tensor field, an antisymmetric tensor field, F. And it satisfies the constraint that allows it to be written as the curl of something. And the something that it's the curl of is A. And you might think that, well, so then why am I not lying to you? If F can be written as the curl of A, then isn't it really true that A is a vector field? And so we've described the massless photon by a vector field, and that's not true. And what's the important part is that the A mu, the field A that appears in the field strength is not a vector. It's under a Lorentz transformation. If you just take the creation and annihilation operators for the photons and you do a Lorentz transformation and ask what does A do, it's a 4-vector up to shifting by a gradient. So it's not a vector, it's a vector up to a gauge transformation. And because it's up to a gauge transformation, the fact that it's not a vector doesn't ruin the fact that f mu nu is a tensor. And so that kind of shows you that if you want to describe things in terms of A, the requirements of Lorentz invariance are going to be forcing you, and quantum mechanics together, are going to be forcing you to have gauge invariance as well, because it's being driven by the fact that the vector potential is not a 4 vector under Lorentz transformations. And that's in practice important, because when we look at the couplings to matter, if we're interested in couplings that are not derivative couplings, they're going to have to involve A, not F, because they're not derivative couplings. They don't go away at low energies. So in particular, the Coulomb interaction has that property. And so if we're going to couple A to something, a 4 vector involving other matter, a coupling like A dot A mu J mu would have been Lorentz invariant if A and J had been 4 vectors, but A is not a 4 vector. So you have to, in order to be Lorentz invariant, you have to ensure that the shifting of A by a gradient doesn't change anything, and that's why the thing you couple to has to be conserved. And so the requirements of gauge invariance in the interactions of massless spin 1 particles are being driven by very general principles at low energies. That's a very powerful. When I was a student, I remember first thinking about gauge invariance as being an assumption that we make, which seems to work really well. And so it's very illuminating that this low energy perspective of massless particles and Lorentz invariance in quantum mechanics is really driving the assumption of gauge invariance. Now, we know that we can organize interactions in inverse powers of scales. And if we did that for electrons and photons, we know that the thing that should dominate at low energies is the renormalizable part, the thing that's unsuppressed by masses. What's the most general thing we can have? Well, given the particle content and symmetries of an electron and a massless spin 1 particle, the only thing we can write down is this, and this is quantum electrodynamics. So we have this low energy perspective is driving a very general understanding of quantum electrodynamics as being the most general thing you could have had at low energies, given you have the interactions of a charged spin 1.5 particle and a massless spin 1 particle. All the theories that we really know and love, like general relativity and the Standard Model, have that property. They're the most general things that can survive at low energies. And the power of that predictiveness is actually very useful to, it's a very powerful point of view to have about the inevitability of various physical laws. Now for gravity, there's a similar story. If you ask, what's the field that represents a massless spin 2 particle? It's not a symmetric tensor. It's actually an anti-symmetric, it's a rank 4 tensor, which has the symmetry properties of the Riemann tensor. And the requirement that it represent a massless spin 2 particle means that it can be written in as various derivatives, 2 derivatives on something that looks like it's a spin, it's a symmetric tensor, but it's not a symmetric tensor. It's only a symmetric tensor up to a specific gauge transformation. So the story for spin 2 is very much like the story for spin 1. And so the gauge invariance associated with general covariance essentially is kind of buried in deep as a consequence of Lorentz, just ordinary Lorentz invariance and quantum mechanics. The story is very similar in that you couple to, if you want to couple a massless spin 2 thing to matter in a way which doesn't go away at low energy, so it's a non-derivative coupling, because h mu nu is not a tensor, it's only a tensor up to gauge transformations, then that constrains the kinds of things you can couple it to, and in this case, it requires it to be a conserved symmetric tensor, and we know that there's only, the Coleman-Mandula theorem tells us there's only one thing like that that you can do that with, and that's the stress energy of the matter. And so the similar power of the low energy limit is working in gravity like it did for electromagnetism. And you can ask, what are the renormalizable interactions between electrons and massless spin 2 things? And in this case, because of the restrictiveness of the requirement that you're coupled to a conserved symmetric tensor, the answer in this case is there are no renormalizable interactions. And so that's actually good news, given that we know that the spin 2 particles, massless spin 2 particles that we know about in life is the most weakly coupled thing that there is. That's a very generic thing that we should be expecting at low energies, is that it shouldn't be coupling to things because it can't in a renormalizable way. All its interactions should be suppressed by some scale. So there's a power there. There's kind of a very fruitful point of view. It's a fruitful way to think about gravity. But traditionally, the way we think about gravity is classically. And so I'm going to put aside the effective field theory story now and kind of give you a reminder of what I think many of you already know about cosmology, focusing on things that will lead to the story, the modern story of structure formation, which is a very beautiful one that's emerged in the last few decades. And then we'll come back to the effective field theory issues at the end, probably tomorrow. This is a natural place to break for questions if there are any questions before I start talking about cosmology. If not, then I'll press on. It's useful in this cosmology part. Part of my judgment call in the rest of these lectures is how much material to use. Because when you're preparing slides, what's nice about doing things on a blackboard is you can judge how fast things are going and what the level is very efficiently. Whereas for slides, you have to do it in advance without really knowing how it's going to land. And so I don't need to talk about everything here if it's all review material. So I kind of I have some leeway as to how much I cover, and so that I normally would judge that based on the questions and so on. So let's start with cosmology. So the basic observation is a kind of I think a one that everybody's heard. There's two observational statements and an inference that you found cosmology on. The first one is that this used to be a principle that for simplicity you'd assume that matter was distributed around us isotropically and homogeneously, and that's kind of like the Copernican principle, the way that Einstein would have thought about it in the 1920s. But really now it's a phenomenological statement. We measure where stuff is, and it's very uniformly distributed around us. That kind of sounds a little bit paradoxical because we look around us, we see stars, we see planets, we see things that don't look like they're homogeneous. But the statement I'm making is at very large scales, when you kind of get much larger than the most nearby things. So we have, one of the things that's been exciting about the last 30 years is that people have done these extensive galaxy surveys where they may measure the distance to them as well as the direction to them to map them out in three-dimensional space. And this is one of the maps that you get from that. This is from the Sloan Digital Sky Survey, where this is not an artist's rendition. This is a map. And the big wedges here are places that it's hard to see because the Milky Way, our galaxy, is in the way. But you see that it's not exactly uniform. There's these filaments and things. So structure has formed, but the farther out you get, the kind of more the smoother it's looking, and the more all directions look the same on an average kind of basis. When you go farther out, we see the microwave background, which I'll come back to a little bit. The microwave background, well, I'll say it right now, that there was a picture. The picture will be that the universe in the past was hotter than it is now, and so in the past, things, if you go far enough in the past, one of the things that a hotter environment will not sustain is bound states. So if you look at atoms, for example, once you're more than 1,000 degrees, atoms have a hard time surviving, in as much as the electrons and nuclei are always finding themselves in forming atoms. That's always an energetically favorable thing to do. But if you're hot enough, things are colliding energetically enough, they're constantly being disassociated all the time. And once you're above a threshold temperature where the average kinetic energy of the collisions is bigger than the binding energy, then on average, you don't form many atoms because you're breaking them as often as you form them. In a world like that, if your temperature is above 1,000 degrees, the universe would be opaque. It wouldn't be transparent to light because now everything is made of charged particles rather than neutral atoms. Very efficient at scattering light, so light will bounce around. And so living in that universe would be like living in a luminous cloud. It would be you wouldn't see your hand in front of your face because the light coming from your hand would bounce around so much. And so there'd be a lot of light. So it'd be like in a fog, but with a light source during the day as opposed to at night. But as the temperature falls through the binding energy of atoms, what happens is that the electrons find the nuclei, then things become dominated by neutral atoms, and all of a sudden the light scatters less, and the universe becomes transparent. So it would be as if you're in the fog and the fog lifts. Then all the light that was there is still there, but now it's moving in straight lines. And so that light is seen. That's what the cosmic microwave background is. It's the light that last scattered from basically hydrogen, which is what the universe was full of at the time, as the hydrogen was forming out of the charged constituents, when the universe was about 1,000 times hotter than it is now. And so the maps like this one you're looking at are temperature maps. The hydrogen at the time was hot, so it had a thermal distribution, and that's been measured. And in what you're seeing here is the temperature of that distribution as a function of direction in the sky, where they've taken out the overall motion of the Earth relative to the preferred frame of this radiation. And what's not shown in these pictures is the scale. The temperature is 2.715 degrees Kelvin, so it's a few degrees Kelvin. The motion of the Earth is about a 10 to the minus 3 of a degree. And then once you've taken that out, what's left here is a 1 part in 10 to the 5 effect. So the red and the blue areas are temperatures that differ by 1 part in 10 to the 5. So it's a very homogeneous temperature distribution, but it's not exactly homogeneous. And so this is giving you an idea that the inhomogeneities at this time in the universe were 1 part in 10 to the 5. So it's a very homogeneous place. Relative to the galaxies, the way to think about this is that we're in the middle. We're looking out, and in redshifts of a few, so that's not very far away from us, are where these galaxy surveys are. You keep on looking, and eventually you see the light from this last scattering from this hydrogen, the microwave background. And beyond that, you can't see because the universe is now no longer transparent. And so the relative scales are that the microwave background is farther away than the galaxies are that we're looking at when we're assessing how homogeneous things are. And the farther away you go, farthest away we can see is the microwave background. It's super, super homogeneous. It's a part in 10 to the 5. Now, the second observation is that that's where they are. What are they doing? The galaxies are all moving away from us, except for about 6. I think less than 10 of them are not moving away from us, and all the ones that are moving towards us are really close to us. Everybody else is moving away. And on average, they're satisfying this Hubble law that their speed of recession is proportional to their distance. So that changes a little bit when you get super far away, but for the most part, they're all doing that. And so that smells like if you ran them back in time, they're all here at the same time, because the ones that are twice as far away are moving twice as fast. Sounds like an explosion. You would have thought that if you had been living next to where a bomb went off, it would not look very homogeneous and isotropic. And so where's the hole? Where's the crater? There is no hole. The things look very isotropic, and that's because a better way to think about this is not that things are moving apart in space, it's that space is expanding. And that's what general relativity tells you should be happening. So what we know is that we believe that gravity is the curvature of the space-time responding to the energy that's inside of it. And for local systems, like for the solar system, the curvature is the curvature given, say, formed by the sun or the Earth. But for the universe as a whole, the geometry as a whole will also respond to the energy density as a whole. And that's described by a metric like this. This is called the FLRW, Friedmann-Lemaitre-Robertson-Walker geometry. It's a geometry which is homogeneous and isotropic, but evolving in time. So it's invariant under rotations in space and translations in space, but it's changing in time. And the example I'm writing down here, it's described by a metric. So the metric is just a rule for a little Pythagorean rule for taking little coordinate displacements and turning them into physical lengths. And curvature is described by the way that rule varies in space and time. And I'm making an assumption here. When I write dx.dx, I mean the flat length of a vector x. And that's, so I'm assuming here that space is flat when I write that metric. The FLRW universe needn't assume that you can actually have a spherical geometry or a hyperbolic geometry. Those are equally allowed. I'm using the fact that we can actually measure, as we'll see, the curvature of space, and it has been measured to be basically flat. And so, and once you go back into the past, it gets more and more flat. So it's one of those things where I'm using an observational feature here to simplify everything. But there is a slightly more general way of phrasing everything that I'm ignoring for simplicity. So all distances are stretching, and in particular, wavelengths of light are stretching. And so the useful proxy for distance and time, or time is really redshift. That's easy to measure. And so the evidence for the recession of the galaxies is coming from the fact that they're redshifting. And rather than thinking of that as being a Doppler effect, it's useful to think of it as the expansion of the universe. And of course, superimposed on that is motion within the expanding universe. So there's a combination of what they call peculiar motion and the overall expansion of space-time. But a proxy for the size of the universe will be the redshift given by this basic rule. So there's two important scales that we're going to track. One of them is typical sizes of things. So that's the physical distances, and that's expanding as the universe expands. The other one is the Hubble scale, defined by the rate of change of the expansion. That A dot over A defines 1 over a time, or 1 over a length in a relativistic context. And so that Hubble distance, H inverse, is a physical distance that is changing in time, but in a way which is different from physical distances that are defined by coordinate differences. And for example, if it were true that the expansion of the universe was a power law, then this Hubble distance would be linear in time, whereas the expansion itself is a different power of time. And so you can kind of see that an important part of the story will be that these are expanding at different rates, and the competition of those rates will be something we're going to want to follow. So when we see the sky, we're kind of looking back along our past light cone. So we're up here looking back. There's slices. Let me show my pointer again. There's slices at different times that we can see. We're at the top looking down at the light cone, and you can kind of see that at different times we're seeing farther and farther away. So that the farther away you're looking, the farther into the past you're looking. And these blue circles here are meant to be, you can think of them as either being physical sizes or the Hubble size. Those are both evolving, they're both growing into the future. So here the Hubble size, let's say, is small, here it's bigger, and here it's bigger because time is moving up in this picture. And so one way to think about what you're doing is that when you look in the distant past, you're seeing a whole bunch of independent Hubble patches, things that are the size set by this Hubble scale. And so there's a sense in which we're looking at a bank of TV sets across the whole sky, where the number of sets is larger the further back we look. And an important property of the Hubble scale is that it's difficult to maintain correlations. It's difficult to generate correlations dynamically on scales that are larger than the Hubble size, because the Hubble size is the size for which the expansion of the universe is the dominant thing in your life, and physical interactions are less important. And so there's a natural sense in which causal interactions will happen typically for scales that are smaller than the Hubble size. And so that means if you see correlations happening across multiple Hubble volumes, you can see multiple Hubble volumes in the past, those are things that you're going to need to explain, because they're not necessarily going to have been built up by ordinary interactions. You know, if you see that the temperature of the room is the same everywhere in the room, that's normally because if it wasn't the same, things would move around to make it the same. But once you look at temperature across places that are separated by multiple Hubble distances, they haven't had time in the universe to know what the temperature was supposed to be that they're supposed to share. So one of the puzzles of the microwave background is that we're looking at basically a whole bunch of independent Hubble patches, and they all share to 1 part in 10 to the 5 the same temperature. And one question will be, why does that make sense? That's part of the structure formation story that we're going to head towards. The temperature, this little plot here is just showing you that this temperature has been measured. It's the black body spectrum. The number of photons as a function of their wavelength is exactly what you'd expect for it's the best measured temperature black body spectrum that's ever been measured. The experimental dots, the error bars on those plots are smaller than the width of the line. So there's very good evidence that this temperature is there, and it's very uniform. So now I'm heading towards how fluctuations form galaxies. And so I want to again emphasize the role that's played by the Hubble scale. and how the Hubble scale is really, how things behave differently on scales that are small and large compared to this Hubble scale. It's an important scale in the problem. And one way to see that why is to look at the wave equation for a field. This wave equation is going to be what the gravitational fluctuations are actually going to satisfy. But if I have a wave equation satisfying box phi equals 0 in this kind of a geometry, the expansion of the universe contributes. There's the usual, if dot is ddt, there's a usual acceleration piece, there's a usual spatial derivative piece, but there's also a piece involving one derivative of time together with one derivative acting on the metric. And so this is a piece which looks like a friction term. And so you can kind of see that if you were looking at in momentum space, there's going to be different behavior depending on which of these last two terms is the important one. So the if you're sub-Hubble, so if your wavelength is smaller than the Hubble distance, this term will dominate this term. And then things will behave like waves, the way that you're used to them behaving. So what'll happen then is that you'll get damped oscillations. But what happens also is that because of this factor of A in the derivative term, the wavelengths are being stretched. That's the redshifting of the wavelength of the waves. And so the longer you wait, the longer the wavelength gets. And what will happen is that things that were originally smaller than the Hubble size will become larger than the Hubble size often in some situations, or in different times in the universe, it'll go the other way, that you might start off larger than the Hubble scale and end up smaller than the Hubble scale. And once it's true that this last term is smaller than this term, then things behave, this friction term starts to win and the oscillation becomes overdamped. And so it just basically freezes. And so the behavior is very different for super Hubble versus sub-Hubble evolution. And so we'll have to keep track of the relative sizes of scales fairly carefully. That damping is generally called Hubble friction. It's just coming because of the expansion of the universe. All right, now back to cosmology. So far we've been talking about the expansion like it's something you get to make up, but the whole purpose of general relativity is to relate the geometry to the energy that's around. So there's an expression which this is the Einstein equation. It relates the stress energy T mu nu of what is in the universe to the curvature of the universe. And with the symmetries that we see around us of the homogeneity and isotropy, the stress tensor, the only stress tensor that's consistent with those symmetries is one of a fluid. And so usually you describe this stress tensor in terms of its pressure and its energy density. So P is the pressure and rho is the energy density. And there's a forward velocity describing the rest frame of the fluid, which is what U mu is. It's something which is normalized to 1 in the geometry. So what we'd like to know is how's the curvature responding to the pressure and the energy density? And so Einstein's equations boil down to these two equations. The top one is the Friedmann equation. It's telling you how the expansion rate responds to the energy density. And the second one is expressing essentially energy conservation. It's saying that the rate of change of the energy density is related to the pressure. And the connection to energy conservation comes if you can think of this, that second equation is equivalent to what's in the box there. So if that's saying that the change in rho a cubed, which is like the total energy, the density times the volume, is related to the pressure times the change in the volume. So that's like the change in the energy is related to the work done. And so that's kind of how you see that second equation is expressing this sensor, which is expressing energy conservation. It's showing you that the work done by the pressure is accounting for the change in the total energy that's associated with that energy density as the universe expands. If I use that second equation, if I differentiate the first equation and use the second equation, you can derive an acceleration equation. And this is what you get. It involves this particular combination of rho and P. And of course, if you think of rho and P as being both positive, which is the natural thing that you would expect for gases, then this has a definite sign. It's negative. And so you'd expect that the acceleration of the universe, the expansion of the universe should be slowing down if it's full of ordinary stuff, right? That's what everybody did expect until the 90s. And the only way you can change the sign of A dot dot is to have the pressure be bigger than minus rho over 3, which means in particular it's negative if rho is positive. And the significance of that is that we think the universe is accelerating. So we think A dot dot is positive now. and not negative. And so that means something like that is going on in the universe. The dominant stuff in the universe is doing this. And the reason we think that is people have been measuring this Hubble law, that if you can measure the distance to a galaxy and the speed of recession, but do it for things that are farther and farther away, you can see how the Hubble law is changing. You can see if the velocity is changing as you look further away, which is to say you look further into the past. And so the way it was been done is with supernovae. So this is a picture on the left is a galaxy, and the star on the bottom left of the picture is not a foreground star in our galaxy. It's a star that's the same distance as that galaxy is, but it's a supernova. So it's as bright as the galaxy. And what's great about these supernovas is that you can see them a long ways away, but they also are believed to be, you can infer how bright they are in a very regular way, so that you can calibrate how far away they are from how bright they are. And when you do that, you can map out distance as a function of redshift, or distance as a velocity as a function of distance. And you get curves like this one on the right. The various lines here are the measurements are the ones at the top. The various lines are various predictions for what you would have expected to see if the universe was accelerating or decelerating or not accelerating at all. And the measurements are consistent with the accelerating option. They're showing you that because the universe is accelerating, in the past, it looks like it was expanding less than it would have done if we just extrapolated back from what it's doing now. And so I always get this wrong. So what's happening is that things are dimmer than you expect them to be, because if you'd extrapolated back and thought about how far away they would be based on how fast they're moving now, you're getting it wrong, because they're actually moving faster now than they were in the past. They haven't gone as far as you think they should have done. And so I guess they're brighter because of the fact that the ones that are farther away, what they measure is the brightness, and then they infer a distance using the fact that they think that they can calibrate how bright a supernova is as a function of its distance. So that sounds weird. How do you get negative pressure? Well, it's not as weird as you might think, because the vacuum should have negative pressure if it has positive energy. What we know about the vacuum is that it's Lorentz invariant, and the only stress energy that's consistent with Lorentz invariance is something proportional to the metric, with some constant or some function of proportionality, but conservation of energy forces the proportionality to be a constant function. So there's some number, rho vac, which will be the energy density of the vacuum, but the pressure is given the energy density is dictated to you by Lorentz invariance. And so, and in particular, if I compare this expression to what we had for a fluid, you can see that it corresponds to the case where P is equal to minus rho. And so that kills the thing that sees the preferred frame or the fluid, because there is no preferred frame if you're Lorentz invariant, and you're only left with the pressure. And that pressure and the energy density are constants in a Lorentz invariant homogeneous isotropic world. So that's kind of weird having negative pressure, but you can kind of see it's also weird having constant energy density if your universe is expanding, because if your density is constant and your volume is growing, your energy is growing. And if you go back to the energy conservation story, you can kind of see that the negative pressure is exactly what you need to allow that to be consistent with energy conservation. So you've got a constant energy density, which means that your energy density is growing. Your total energy is growing because your volume is growing, but you're doing negative work because your pressure is negative, and just the way you need to extract the energy from the expansion of the universe. And so this Lorentz invariance of the vacuum is very generally pointing you to a situation where pressure, that's a physically reasonable situation where pressure could be negative, and it's consistent with the various conservation laws we think should be true. And of course, no one says the vacuum can't gravitate, so it's not. It seems not a stretch to imagine that there's a vacuum energy that could be gravitating. All right. So having said that, now we want to head to this very successful picture of cosmology that's built around that. And so the hot Big Bang model is the model that people are always talking about. They call it lambda CDM because there's got various. You'll see that there are the ingredients of one of the things that's amazing about being alive now is that we can actually measure the total energy density in the universe, regardless of whether you can see it or not. So we know how much is out there, and we know that there are various ingredients that we don't understand, one of which is the vacuum energy, that's what they call lambda, and there's also dark matter. And so this hot Big Bang picture basically takes the observation the universe is expanding, And it says, so if I ran it backwards, I would have expected it to be smaller, hotter place. So the Big Bang model says, let's suppose that we can extrapolate that all the way back to where we have elementary particles in the universe that are just a hot soup of elementary particles. And let's imagine now running that forward. Does it look like what we see? And the amazing success of modern cosmology is that it looks very much like what we see. And so what you test for the most part when you do that is you can predict how fast the universe cools. But the most interesting thing is the prediction for that there have to be relics. We talked about the universe being in a place where atoms at one point formed. That's a special case of relics forming. That at the very early universe, if the temperature was ever higher than 1,000 degrees, we only would have had a soup of elementary nuclei and electrons. But if the temperature cools below 1,000 degrees, then atoms start to form, neutral atoms start to form. And so the universe after that looks different because the atoms have formed and you no longer have the free gas of electrons and positrons. If you extrapolate further back to something like 10 billion degrees, the same thing would have been true for nuclei. The protons and neutrons above that temperature no longer form nuclei. They form nuclei all the time, but they're being knocked apart as often as they form. So you would have had a soup of protons and neutrons and electrons as opposed to a soup of nuclei and electrons. And again, what will happen is as you pass through 10 billion degrees, nuclei will form, and then those are the relics that are forming as you pass through that threshold. And the amazing thing about cosmology is that there's observational evidence for both those things having happened. So the evidence for the atoms having happened is the microwave background. We see the microwave background. We see where the universe became transparent because the light at that epoch is still around. And there's evidence that the nuclei formed because when that process happens, you form the different light nuclei with different abundances. You can calculate their abundance rate because there's a competition between nuclear reactions and the expansion of the universe, which controls how fast things cool. And you can compare that with what you measure for the primordial nuclear abundances. And you can do that for 5 or 6 light nuclei, various isotopes of helium and hydrogen and beryllium and lithium. And the fact that it works for all of them, the one number captures all of them, the one number being the total density of nuclei, which controls the reaction rates. That one number gets these various species of nuclei all correct at the same time. That tells you that probably nuclei form that way, but it also tells you, gives you a measurement as to how many nuclei there are in the universe, which is relevant when we think that there's other things in the universe besides nuclei, because it's good to know how many nuclei there are independent of whether you can see them or not. So it's a very, very attractive story, and I'm going to give you just some snippets of it heading towards galaxy formation. So we've got a fluid. We know there's many things in the fluid. There's all the elementary particles we know about, going back to where nuclei formed. The important thing for the expansion of the universe is not the details of their chemical composition, it's more their kinematics. So what's the equation of state of the fluid that they satisfy? So we've seen that the vacuum is something which has a very specific equation of state. The pressure is minus the energy density. But for relativistic matter like photons or anything for which the temperature is much bigger than the mass, we know that they behave like photons do, and they have the property that their pressure is 1/3 their energy density, and those things are both proportional to the temperature to the 4th power. Because if everything's relativistic, the biggest scale in the problem is the temperature. All the other scales like masses are much smaller. And so on dimensional grounds, both rho and p would have to be proportional to the temperature of the 4th. And the constant sigma is a number that's not changing in time. Or it's changing in time depending on how many species of relativistic particles you have. And non-relativistic matter, that's going to look, if it's not interacting very strongly with itself, is going to be look like an ideal gas. So the pressure will go like proportional to temperature. And the energy density will be dominated by the mass of whatever that thing is because it's non-relativistic. So the rest mass will be the biggest energy. And so N here is the number density of these things. And so that shows you that the pressure should be negligibly small compared to the energy density because the temperature is normally negligibly small compared to the rest mass for non-relativistic degrees of freedom. Now, all those ingredients are known to be there, and their abundances now are known. And so here's a cartoon of what we know. So we know both the fraction of what's out there in these various kinds of species of matter. So capital omega will be the abundance, the energy density in these things divided by the total energy density that we know is out there. And that total that we know is out there is about 10 to the minus 29 grams per cubic centimeter. That's the units the astronomers actually use. And so part of the story is, why do we know the total abundance of what's out there? And the reason we know is that it's related to, relativity relates that to this curvature of space, and we can measure the curvature of space. So the abundance that's seen to be in the various components I was talking about is this, that most of it is the vacuum energy, about 70%. About 30% is the non-relativistic stuff. And then the radiation seems to be something like a 10 to the minus 4 contribution to the total energy density of the universe. The non-relativistic stuff wins a lot because its rest mass is very big compared to the energies of things. Even though there are a lot of photons around, there are more photons around than there are baryons, let's say. Each of them has got less energy on average because the temperature now is less than the mass of a proton, for example. The plot on the right here is showing you evidence, which I won't go into too much here. The vertical axis is the fraction of vacuum energy. That's omega lambda, is what I'm calling omega vac. And across the bottom here is the fraction of the energy density that's in non-relativistic matter. The diagonal black line is the total energy density is equal to 10 to the minus 29 grams per cubic centimeter squared, because it's the sum of these two things is fixed. The blue oval is the abundance of both those things that you need to account for the measurements of the acceleration of the universe that I alluded to using supernovae. There's a lot of error bars in there, and getting agreement with what's seen puts you in the blue oval. The green stripe is essentially it's one way of measuring the total amount of non-relativistic matter, basically independent of the presence of dark energy or the vacuum energy. That's why it's basically vertical, this green line. It's the best measurement we have of how much non-relativistic matter there is. And this orange line is what you need to be consistent with the microwave background. And they intersect at a place which is where we believe we are. And so that's where the 70% dark energy or vacuum energy and 30% dark matter is coming from. And it's also lying on this black line, which is saying that the total energy is 10 to the minus 29 grams per cubic centimeter. So I'd like to kind of take a little deviation to emphasize two things. One thing is the non-relativistic matter contains both baryons, the stuff we know about, which is about 5% of what's out there, and stuff we don't know about, dark matter, which can't be baryons because the formation of nuclei constrains how many nuclei we can have, how many protons and neutrons can be out there. So we know that there's more stuff out there than can be ordinary protons and neutrons. But I'd like to also focus on where the CMB curve comes from and why is it measuring the total energy of the universe. What's happening there is we're over here, we're at the bottom of the picture. We're looking at the microwave sky, the microwave background. And the difference between a red area and a blue area is a hot area and a cold area. That's a sound wave in the hydrogen that was forming when atoms were forming back when the universe was 1,000 degrees high. And so with the distance between them is the distance that sound and hydrogen can travel in the time that there has been available to it before that in the universe, which is not very long at that point. The universe is only hundreds of thousands of years old then. And so it's like somebody held up a ruler for us at the other side of the universe, which is we know a lot about how far sound can travel in hydrogen. And so we know how far the sound horizon is, how far sound can have gotten in the time available to it at that time. And that's how big these little circles are that I'm drawing on the picture. So now we have a lot of information because we have a known distance at the other side of the universe. We know how far away the other side of the universe is because if we know how fast the universe is expanding, that's what the thing that says Hubble length here. That's telling us how far away the microwave background last scattering surface is from us. Once we measure the rate of expansion of the universe, we know how far away that is. And we can measure this angle, that is the angle between the hot and the cold area. And now you have a lot of information about this triangle. This yellow triangle is an isosceles triangle. And in school, you learned in a Euclidean geometry that if I give you one side of that triangle and the angle, that determines the triangle. But I've given you two sides and the angle. So that means you can decide whether or not Euclidean geometry works or not. And it does, it turns out. And so that's the information that we're living in a flat space-time, or space at a given time is flat. is coming from measurements like this, that by the microwave background, the fact that we know the distances involved are to do with how far sound goes in hydrogen, but it's on the other side of the universe, and the light had to travel through the universe to get to us, tells us what the geometry of space is in between. And that the fact that it's flat then tells us how much stuff is in the universe, because Einstein's equations link the curvature to the total energy density. So that's kind of how we know that the density is this, what they call the critical density. It's 10 to the minus 29 grams per cubic centimeter. And of course, it's more complicated than I'm making it sound. You know, you have a model of the expansion. It involves some number of parameters, and here they are. Here's a list of them. And you're fitting it to many, many observables. And what's important is that there's more observables than you have parameters. So it's a redundant determination of the parameters. And the ones that we're going to follow are the ones that, you know, we're going to follow. Omega B here is basically the baryons, the fraction of baryons in the universe. Omega C is the dark matter abundance in the universe. H naught, we've talked about, that's the Hubble expansion rate. Omega M is the total non-relativistic fraction of stuff. So omega M is not independent of omega B and omega C, and you kind of see that that works. The other two things that are appearing here, AS and NS, are to do with the primordial distribution of density fluctuations in the universe, which I'm going to get to. That's where we're heading. Those are important parameters that we can measure in the universe, and they are describing how galaxies, they're controlling the distribution of galaxies we see around us. And I'm heading towards what those parameters are and why we care. Right. So now everything goes back to general relativity. We know how things evolve. This is our statement of what the expansion of the universe is. And the equation of state that the matter satisfies controls the expansion rate. And you can integrate these equations if you know the equation of state, so you know what the ratio of the pressure to the energy density is. You can integrate this equation in the box there and learn how it changes as the universe expands. For the vacuum, it doesn't change. For non-relativistic matter, the energy density falls like 1 over the volume, and that's kind of intuitive, that you've got a total amount of energy, which is the mass of all these things, and you just dilute it as the universe expands by 1 over the volume. So the density goes like 1 over the volume. And for radiation, it goes like 1 over 8⁴, which is to say the number of photons is falling like 1 over the volume, like it is for baryons, but it's also true that every individual photon is redshifting. And so there's an extra suppression because of that. And then given that information of how rho depends on A, you can figure out what the expansion rate is. And that's what it turns out to be in these various situations, depending on what's dominating the universe. And if these fluids, the relativistic and the non-relativistic and the vacuum, don't exchange energy, then they will be separately conserved, and the story I've told you will apply to them each separately. And that leads you to predictions for what the energy density will do as a function of time. This is the log of the energy density against the log of the size of the universe, and 0 is where we are now. The vacuum didn't do anything. Matter falls like 1 over 8 cubed, and radiation falls like 1 over 8⁴, which is to say faster. And then if they're basically not exchanging energy much, then the total will just be the sum of these things. So it'll start off being dominated by radiation, then it's dominated by matter, then it's dominated by the vacuum. And right now we're in a regime where it's just starting to become dominated by the vacuum. So the various events that I've talked about are on this picture. We're here now. Nucleosynthesis is back when the universe was 10 to the 10 times bigger, so it's over to the left of the picture. This place where radiation and matter exchange roles as being dominant is important. That's radiation-matter equality. The microwave background is that the atoms are forming around here. They're at a redshift of about 1,000 when the temperature was where atoms would form. And then galaxies are forming in between here somewhere. And that's the story we're going to head towards here now. So let's focus on structure formation. I can see that I'm getting towards the end here. I should pause for questions in case there are any. Otherwise, I'll power through. Yeah, there's a question, I think.
I was just wondering if you're going to say something about the Hubble tension.
Not directly yet. It's but I could if you like. Yeah. So why don't I go? I'll go a little bit farther and then come back to that. It's I'm taking it as being given that the Hubble tension, the Hubble value is a value, but I'm not. I'm right now taking the point of view that I'm not getting into the errors of that are associated with any particular way of assessing it. And of course, the tension you're talking about, for those who don't know, is that if you measure the expansion of the universe using local galaxies, you get one number. If you do it from the microwave background, you get a different number, and they seem inconsistent with one another. And there's a puzzle as to why that's true. And it might mean that there's the errors in the measurements are being underestimated in one way or another, or it might mean that there's some physics going on in the picture that I'm not telling you about, which is making them disagree with one another.
Thank you.
And I think, and no one knows which is right. I think right now is the fair thing to say. So I'm ignoring it because I really want to tell you that I'm trying to confirm in people's mind the standard story of structure formation. That's which is a very beautiful thing and which particle physicists often don't see. So the question is, where do galaxies come from? And the answer is gravitational instability, basically. We know that the universe was not exactly uniform. We know that the microwave background has fluctuations in it. They're small, but they're there. And then gravity amplifies that, because if you have a little overdense region, things fall towards it and it becomes even more overdense, and then that'll basically grow. And the main message is that that's a really good description of what you actually see. There should be correlations between what you see in the microwave background and then what you see in the galaxies that came later. That the overdense regions in the microwave background should be the things that correspond to overdense regions in the galaxy distribution, and those things are there. That BAO thing I didn't explain about the measurement of dark matter is one of those correlations. It's called the baryon acoustic oscillation. It's a very, very beautiful picture that there's a very deep correlation between what we see in the microwave background and what we see in galaxies. And the way that's normally conveyed is statistically. You take the density, overdensities, and you Fourier transform them, and you look at their correlations in space, rather than asking where we are compared to a particular instance of how the inhomogeneities might have been. And so that statistical distribution is characterized by this, what's called the power spectrum, what I'm calling P here. And if you know the distribution of densities, you can figure out what the predicted power spectrum is, and that's something which has been measured, and it's been measured at many scales. It has this shape. For small wave numbers, it grows roughly linearly with k. And then there's a characteristic scale where things change, and then it starts to fall like 1 over k cubed. And the story I'm about to tell you is that the structure of this is phenomenologically described very well by this expression. There's 4 numbers involved here. The numerator is telling you what's happening for small k, and the denominator is telling you how things change when you go to large k. And the argument I'm going to give is that the first 2 things, those are telling you what the initial conditions were. That's what primordial fluctuations gave you. That's what we're going to explain with quantum fluctuations. And the second thing is about gravity evolving things forward in time, in late times, where we actually see things going on. And the conversion from linear in k to 1 over k to the cubed is something which we understand, where that how gravity would imprint that on the sky. All right. So this slide is mostly making the connection that the microwave background is not independent of this power spectrum that I'm talking about. One way to think about the way the temperature changes in the microwave background, there's a paradox in the microwave background. I've told you the microwave background forms as soon as atoms can form, but the criterion for atoms forming is a criterion of energy. So you might have assumed that if you're seeing the surface where atoms are formed, that by definition will have the same temperature everywhere. How can there be fluctuations in that? And one way to think about that is that what's happening is the surface of last scattering does have the same temperature everywhere, but the photons have to climb out of gravitational potential wells if they happen to be living in an overdense region, whereas photons that are not in the overdense region don't have to climb out of those wells. And so that's what's imprinting the temperature distribution. So there's a connection between the temperature distribution and the microwave background and this density distribution in 3 dimensions that I'm talking about, this power spectrum. The same thing happens when light falls into the gravitational well of a galaxy, which I'm kind of drawing here in the bottom. But normally the red shifting that happens when you fall in is canceled by the blue shifting blue shifting when you fall in is canceled by the red shifting as you climb out. And so there's the main thing that's happening is as you're climbing out of potential wells at the surface of last scattering. So we're over here seeing the light arrive. It's leaving from a surface which has a definite temperature, is one way of thinking about it. And then some of it redshifts, some of it doesn't, depending if there's a local overdensity nearby. So there's a connection between the temperature distribution and the power spectrum. Good. Now, this last part, which I'm not going to have time for, because I can see that right now I'm at 9:21. So I'm going to press on for a couple minutes and then I'll stop. I want to get to there's 2 points I want to make here. One of them is, how do you understand that power spectrum, the shape of it? And then what do you know about the primordial part of it? That's the thing that quantum effects will influence. So it's all general relativity. So we just go back to solving Einstein's equations. But now what we do is, instead of solving it for the universe as a whole, we look at fluctuations around those homogeneous solutions. So that what I'm calling G bar and T bar here are the things we've been talking about till now. And now we're looking at fluctuations which depend on space and time, as opposed to just being depending on time. There's a lot of freedom in how you describe these variables, because famously the metric is generally covariant. So there's gauge transformations you can make. And so what you normally do is you classify the fluctuations in the metric according to their rotational properties, because they do not mix at linear order. So there's a scalar piece, which is the top part. There's a vector piece, which is the bottom part. And there's a tensor piece, which is the third one. I'm writing out what the fluctuations of the metric are. And these functions all are defined to be divergence free. And now if you ask what changes they all change in general when you do a gauge transformation. These combinations that I'm showing you here are the ones that are gauge invariant. The quantities B and E and W you can set to 0 with a gauge transformation if you like. And so the ones that we're going to follow are these remaining ones, phi, psi, and V. And of those are, that the metric gravitational waves are described by tensor fluctuations, what I'm calling Hij here. These other things are not gravitational waves. These are constrained variables. They're like the Newtonian potential. They're tied to whatever matter is doing. And in particular, 2 combinations of these 3 things, V, psi, and phi, are tied to things that are 0 in a simple cosmology. So V and the difference between psi and phi typically are not being sourced by matter. The only thing that really matters is the Newtonian potential, which I'm calling phi here. And so what we're going to be interested in following are the evolution of the tensor fluctuations, or the gravitational waves, which are the tensor part of the metric fluctuations. This is what the Einstein equation predicts they should satisfy. And we're going to be interested in following the Newtonian potential, which is going to, in the non-relativistic limit, will just satisfy what Newton would have said. It's going to satisfy Poisson's equation. It's going to be related to tied to the total density of matter. Now, the equations of motion of the matter are also there, and in the non-relativistic limit, those are the ones for a fluid, and the Einstein equations become the non-relativistic ones like they're supposed to. And those are actually adequate for understanding the structure of matter, because the important things that are doing it are being amplified are non-relativistic. So this is where I'm going to stop, because I could see that I've got like 7 minutes left, because this is a natural place to break. The plan for the rest of this topic will be, you can solve these equations and you can ask, under what circumstances do you get this instability I'm talking about? The ability of gravity to amplify fluctuations should emerge as solutions to these equations. And they do, and they predict how fast things grow. And we know how long we've had to have them grow, because we've seen the microwave background is very smooth. We see galaxies around, and there's only a fixed amount of time for things to happen. And part of the evidence for dark matter is coming from the fact that there otherwise would not have been, without dark matter, there wouldn't have been enough time to form galaxies. So that's that structure of the point of this part of the lecture is that there's a consistency story that says that the amplification of the perturbations that you see in the microwave background to give you galaxies works, and it's consistent with the shape of that power spectrum that I showed you. And the fact that works gives you confidence that there's something to be explained. It works if you start off with the right pattern of fluctuations. And the ultimate goal of this line of argument is that quantum fluctuations give you a good description of those primordial fluctuations too. So I'll leave that part of it to the beginning of the next lecture. My plan next lecture will be to finish this story, to close out the structure formation and primordial fluctuations. And I'll do it in a bit of a bridge form, because I can see that time is going to be an issue. And then I'll get to the issues that story raises in quantifying. What we want to do is quantify what are our errors in making quantum predictions in cosmology, and that's what effective field theories are good for. So that's where we're going. There's a few minutes left for questions, should people wish to jump in, and I'll stop there.
Thank you very much, Cliff. Any questions?
You told me that the fluctuation of the metric can be not symmetric. Why it cannot be symmetric?
Sorry, I didn't mean to say that. If I said that, the fluctuations of the metric are symmetric. I think what you're thinking of is early on, very beginning of the lecture, I said that that the fluctuations of the metric are not a symmetric tensor. It's definitely symmetric, but it's not transforming it like a Lorentz tensor. That's the main message. In the same way that the vector potential in electromagnetism is not transforming like a 4 vector. It's a symmetric tensor up to gauge transformations is the statement. But it's certainly symmetric. Definitely symmetric.
Thank
yeah.
you very much. Sorry.
Yeah. I'm glad you asked that because that's an important thing.
This is quite a naive question, but when we write down the equation of state, which is metal density equal omega pressure, why we consider they are linear? I mean,
oh, just mostly the way I'm arguing that is. Sorry, let me go back to that slide. I would argue that as just being a consequence of just experimental fact that the main options for what's out there are. Let me go back to those equations of state. You know, the main options are basically the vacuum. Where are we? Here we go. We know the vacuum seems to have energy because we see the universe accelerate, and it happens to be true that the pressure in that case is minus rho. For relativistic matter, we know that basically on dimensional grounds, pressure and energy density both have to be proportional to t to the fourth, and so that makes the ratio of them independent of temperature and so independent of time. And it turns out that in that case, the ratio is a third because if you're relativistic, you're scale invariant, and if you're scale invariant, the trace of your stress tensor is 0. And so that tells you why the ratio has to be fixed to be a third in that case. And if you're non-relativistic, the pressure is basically 0. And so in that case, it's also true that the ratio pressure over energy density is effectively a constant because it's 0. It's really not 0. It's really the temperature divided by the mass, but that's kind of a subdominant effect. That's an order of v squared effect for non-relativistic motion. So it's just really, there's nothing in principle that says that pressure has to be proportional to energy density. But for the three things that we know are in the universe, radiation, matter, and the vacuum, it happens to be true that the pressure divided by the energy density is a constant.
Thank you.
There are exceptions to that. Actually, that's a good question because, I'm treating, say, the radiation and the matter as if they're independent of one another, but you know that in practice, at various times, at specific times in the universe, they won't be independent. So in the early universe, the electrons and the baryons that are charged will be coupled in equilibrium with the photons, and then they'll do things together. So they will exchange energy. And so then the equation of state for that combined mixture can change. So there will be specific times where that assumption has to be checked, and it breaks down at specific times. And then when it does, it's interesting. But more broadly, in the grander sweep of things, it happens to be true that it's constants.
There are any other questions?
Yeah, I have one live question. So in your when you talked about the dark energy, you said that the vacuum is gravitating by
Yes.
considering the gravitation. So does it mean that the usual definition of the vacuum should be modified by just defining the vacuum as annihilation, take annihilation goes to zero? Because in
I see what you're saying.
Yeah.
So no, it doesn't, in the sense that this is a prediction of that picture. And I should also say, we don't really know what the dark energy is. And so the assumption that people make in the hot Big Bang, they're assuming it's the vacuum energy. So they're assuming that equation of state is what's going on. And it seems like it describes very well what they see, but we have no independent experimental verification that that's really what the dark energy is. I can show plots of the people can constrain the equation of state of the vacuum energy, and it's consistent with it being the vacuum gravitating. Mm-hmm. But for your question, what you're thinking of is that the vacuum has to be an energy eigenstate. That's true. But it doesn't have to be a zero energy eigenstate. And so the way to think about it is that every mode of the field is like a harmonic oscillator. And so the ground state of a harmonic oscillator isn't zero energy, it's got a 0-point energy of 1/2 omega. And essentially the vacuum energy that you're seeing here is, one way to think about it is it's the sum of that 0-point energy summed over all the modes of the field. Now that sum diverges. So there's a question then of should that be renormalized, that divergence, because it's dominated by the shortest possible wavelengths. And the answer is it can be renormalized, but the thing it's renormalized into is the energy density of the vacuum. And so there's a parameter in your problem, which is the energy density of the vacuum, and that's not inconsistent with the picture of the vacuum as being annihilated by the destruction operators. And ultimately, that's because the energy density is not the energy. So the energy density can fluctuate because it's something which is not it doesn't commute with the total energy.
Okay, so the other question is, in your constellation or this continuum, I mean, we are approximating this universe as a continuum, right? And using some fluid approximation. Is it always valid?
So far as we know, yes. There's no evidence that it's not valid. People can ask at very small distances if it breaks down, and that it might be true that it does break down, but there's nothing. Cosmology is really measuring the largest possible scales, and there's no evidence that it's breaking down in cosmology. There are things we don't understand in cosmology, like the question about the Hubble tension. There are things that could be wrong with this picture, and the way that they will emerge is inconsistencies. If different ways of measuring the same thing, giving you different answers is kind of one of the smoking guns for something's going wrong, or that there's an error, a measurement error. And it's the hard thing is deciding which is which. But so far, you'll see when we talk about effective field theories for gravity that the things like the discreteness tend to be short distance things, and they are amongst the things that decouple from long distance things. So the long distance picture tends to be very uncomplicated by the quantum gravity conceptual issues that could be very well be there, but at small distances.
Okay. Yeah, thank you.
Thank you.
Any other questions?
Yeah, I have a question. From the measurement of this cosmic microwave background, so is it possible to tell exactly when the structure formation has started?
Yeah, that in a sense, yes, and that's my next topic will be that, because what the picture will be that it actually it's been going on right from the get-go. But the important thing I haven't said yet, but which I will say next time, is that the efficiency of gravity amplifying inhomogeneities is much higher in a matter-dominated universe than in a radiation-dominated universe. So what happens is that things grow, but they only grow kind of logarithmically with time until the matter starts to dominate the universe, and then they start to grow much more quickly. So in that sense, we know that there's a time when growth really starts to kick in, and it's a very specific time, which is when matter and radiation had the same abundance, and that's a redshift of 3600. And so things start then, and then they have to finish by the time galaxies are formed, which is before now. And so there's a window in which everything has to happen. And what's happening is that the description of the galaxies that you get from that picture works very well, assuming that there's dark matter. If there had been no dark matter, it would take longer for the matter to dominate the radiation because there'd be less matter. And if you had no dark matter, there would not have been enough time for this growth to amplify things to become galaxies, given that they had to start as small as they were at the microwave background. So one of the evidences for dark matter is that you had to actually go back to redshift 3600 and have things start then in order to have enough time to have everything be amplified to become galaxies now. So what I haven't told you yet is a very beautiful, consistent picture with a lot of facets to it, which is to do with the fact that there's a specific window when things will grow. Things were growing kind of at some level very slowly until radiation matter equality, but after that, everything grows. And it all has to happen then.
Okay, so in a sense, we have to definitely produce the dark matter before matter radiation equality. I mean, we cannot delay the production of dark matter after that, right? I mean, we cannot produce
Right.
dark matter after matter radiation equality.
Right. So if you had a theory where so there was some exotic matter, but it was all radiation, or very relativistic, and then for some reason it turns into non-relativistic dark matter, but late in the universe, later than normal, then you would effectively be saying that radiation is bigger than we thought and matter is less than we thought, and radiation matter equality would be later, and then it would be inconsistent with structure formation. So there's an important constraint there on when the dark matter had to be available. And it has to be available to cluster before the microwave background is visible.
Thank you.
Good questions.
Any other questions? Okay, I don't see any more. No, okay, so I don't see any more. So let's thank Cliff again. Thank you very much.
Thank you again. See you tomorrow.